Howdy. Today, we will be presenting SIRIUS, a flat data center network with nanosecond optical switching. For today's agenda, we will first be going over what SIRIUS is and what it does. Then we will move on to its architecture. And finally, we will discuss and evaluate the benefits and drawbacks of SIRIUS. Now, if you are familiar with Moore's law, you'll know that electrical switches are said to double their bandwidth approximately every 2 years, with little to no increase in power and cost. However, people have begun to observe a slowdown in Moore's law. This is predicted to come into full effect within the next couple of years, or that it's already in effect now. On top of this, we are also seeing an increase in the amount of cloud traffic, the amount of which seems to double every single year. This growing gap between the available bandwidth and the amount of cloud traffic seen is only expected to get worse and worse. We can see this as software-driven workloads that typically occur on the CPU are beginning to become more hardware-driven. An example can be seen in AI or ML technologies, where deep neural networks need much more processing power and speeds that can only be found in things like TPUs and GPUs. So overall, the combination in the slowdown of Moore's law, as well as increased cloud traffic, will only increase the power consumption and cost of using electrical switches. So this is where SIRIUS comes in. Instead of using electrical switches, SIRIUS offers an alternative in using optical switches. So instead of routing electricity, SIRIUS routes light waves through its special passive core or grating, also known as array wavelength grating router. Light waves are routed through the passive core and into their desired destination ports. Depending on the light wave that is shown through, will determine which port the light will be diffracted or routed to, along with the data being encoded on the light wave. So let's say, for example, we've shown a red light through the passive core. This will be routed to some port like port A. But if we change the wavelength, it will be routed to some other port like port B. All of this is done within nanoseconds. So unlike electrical switching, optical switching is not bound by Moore's law and does not suffer from a slowdown. Instead, its switch capacity is expected to only increase over time instead of tapering off. So overall, what does SIRIUS aim for? Well, one of SIRIUS's goals is to eliminate the need for switches and transceivers altogether, thus reducing the total power consumption and cost that would typically be seen in traditional networks. Another one of SIRIUS's goals is to be able to operate at hardware speeds, thus resulting in super low latency times, as well as increase in amount of available bandwidth. And lastly, SIRIUS aims to be future-proof. So while electrical switches are bound by the slowdown of Moore's law, they require to be upgraded across generations, whereas SIRIUS does not require as many upgrades as frequently, or if rarely. Now on to SIRIUS's architecture. So as we've seen before, light waves pass through the passive core grating and are routed to its respective ports. The number of ports available are determined by the amount of wavelengths that can be produced or tuned by a single laser. However, the switching mechanism between changing to different wavelengths is too slow. This is because lasers need to be tuned to different currents in order to produce different wavelengths. In order to address the latency seen in switching to different wavelengths, the SIRIUS team has developed a different method known as disaggregated tunable lasers. So instead of changing the wavelength of a single laser, we have a bank of several lasers instead. Each laser within the bank will create a different wavelength, all of which are completely unique from each other. Basically, we are abstracting the usage of several different lasers and wavelengths to act as if it's a single laser or source of light that is changing its wavelength. So when we want to select a specific wavelength in order to route, we will use a wavelength selector. As you can see here, the laser bank is casting different lasers or wavelengths to the wavelength selector. And within the wavelength selector, that consists of an array of semiconductor optical amplifiers, or SOAs. These SOAs essentially act as gates. So when we want to activate or route through a specific wavelength, we simply turn on that respective SOA or gate while turning off the other gates. Because we are dealing with light waves along with the switching mechanisms of SOA gates, the whole process can occur within nanoseconds. In combination with using tunable lasers, the routing speeds for these lasers are also made faster through SIRIUS's flat topology. So instead of a hierarchy of switches and nodes that we typically see in a traditional network, SIRIUS flattens all of it down into a single layer. Within this layer consists of gratings that allow up to thousands of nodes to be connected and communicate directly to one another, just as what we would see in a traditional network. These nodes are connected to these gratings and ports through uplinks. Within each uplink contains a tunable laser. So by changing the wavelength through this laser, nodes are able to send data to any port or other node that is connected to the same grating. So in practice, a single layer will consist of multiple gratings and allow for nodes across different gratings to be able to communicate to each other. So for example, on the left here, we see how node 1 is connected to grating 1 or G1. We can also see that through G1, it's able to communicate with nodes 1 and nodes 2 from the right. Additionally, node 1 is also connected to grating 3 or G3, which allows it to communicate with nodes 3 and nodes 4 and so on.
So I'll be talking about other core architectural innovations in Cyrus, basically how it handles routing and scheduling without buffers and centralized controller. As we know that Cyrus uses passive optical components that cannot store and queue packets. So which means that if two nodes try to send to the same destinations at the same time, there is no buffer to handle. So here we need a coordinated scheduling and routing, which are like both important for the whole architecture. So what's the solution? So the solution is Valiant load balancing and cyclic static schedule. So let's see how this Valiant load balancing works. So here, as you can see, like these are the like Torre, Torsi, Torvi, these are the nodes. Here, like every packet is being sent to a randomly selected immediate node first. So Torre would, to send a packet from Torre to Torbi, first like it will send the packet from Torre to Torsi, and then Torsi would send the packet to Torbi. That is the final destination. So basically, this detour flattens the traffic matrix and spreads the traffic evenly across the network. So as you can see in the diagram, each transmitter cycles through destination on a fixed timetable. So if there are 100 nodes, suppose, each node connects to a different one in a round robin manner. And every node knows this schedule ahead of time, so there are no conflicts. No conflicts happen. Congestion control. So Cyrus uses a unique distributed request grant based congestion control system, which is designed to prevent packet collision at intermediate nodes, because we know that buffer overflows would be problematic here. So it happens in a like three-step process. Firstly, queue inspection. Here each node looks at its outgoing packet, and then for each one it basically picks a random intermediate node through which it sends a request to ask for a permission to forward it to next one. The secondly, we have request evaluation. When intermediate node receive multiple requests from sources, for each destination it checks basically, am I already queuing too many packets to this destination? If not, it sends a grant back to one requester. And thirdly, grant handling. When a node receives a grant, it moves the packet into a virtual queue. Basically, it gets ready to be sent during the next epoch. So this approach gives us few benefits, like it has like no more than queue packets which are queued per destination, and this system is fully distributed, so we do not need a centralized controller. Let's wrap up with everything we have explored about Cyrus and why this architecture represents a huge leap forward for the future of data center networks. So as we conclude, it gives us like nanosecond scale switching. So we know that like traditional optical switches operate at millisecond or even microsecond scales, but this framework Cyrus it achieves 3.84 nanosecond reconfiguration latency using tunable lasers and caching techniques. Second one, co-design hardware and protocols. So routing, scheduling, congestion control, and even time synchronization are all designed with the physical hardware. This enables us with like such low latency and reliable behavior for the data centers. And then third, massive scalability and efficiency. So this framework can scale up to 24,600 racks. So that is like larger than the biggest data centers today. And it does this while reducing network power and cost by up to 77% compared to closed networks. Fourth one, future proof and tolerant. So because Cyrus uses a passive optical core, there is no dependency on CMOS or Moore's law scaling. And since it's robust, faults only degrade a small portion of network bandwidth, and thus the network can dynamically reconfigure around failures. So I'll be giving you like a two concept-based examples, like firstly distributed deep neural network training. So let's suppose that we have a in a 1000 GPU training cluster, each GPU generates multiple terabytes of traffic. So this much of traffic traditional networks cannot handle and can't switch that much fast. But Cyrus can reconfigure optical paths at nanosecond granularity, keeping GPUs fed without wasting cycles. Second example is like disaggregated memory access. So when memory and computer are physically separated, so accessing the memory becomes latency sensitive. But this framework ensures that data moves between CPU and memory racks fast enough to feel almost that it's local only. So few of the drawbacks which we could come up with are like firstly, this framework adds like one extra hop to every communication. So it basically increase end-to-end latency and create dependency on intermediates. So overall, this could degrade performance for latency sensitive flows like short RPCs, that is remote procedural cells or real-time analytics. Second drawback is it could be challenging in multi-tenant cloud environments. And the third one, the components like lasers are non-trivial to build, so it may be expensive and require tight calibration for this type of framework. Thank you.
Thank you, Rishabh. A key challenge for fast optical switching is achieving fine-grained time synchronization, necessitating an accuracy of less than 100 picoseconds. Many existing synchronization protocols either lack the required precision or add complexity, increasing costs. The Sirius network addresses this issue by using a passive core and a cyclic schedule to implement a novel time synchronization protocol with minimal complexity. The core network is passive, so there is no active switching logic involved at the center. We can think of the passive core as a central hub. It just lets light through, so timing only needs to be coordinated at the edges. This is why the nodes can afford to not be super accurate by themselves, but they should stay in sync with each other to ensure that the message arrival time at the AWGR is coordinated. These nodes synchronize between themselves with the use of phase locked loop or delay locked loop protocols. In a simplified implementation, the leader could broadcast its clock to other nodes in a cycle. To elevate robustness, Sirius rotates the leader role periodically by conducting a round-robin approach. This automatic leader switching allows for quick recovery if a leader fails, ensuring minimal disruption and preventing noticeable clock drift. Now, let us go over some results. The flat topology of Sirius replaces multi-layer ESN with a single passive optical layer and cuts power consumption and costs by 75%. For example, in a 4,000 rack data center, you can think of an traditional ESN consuming about 500 watts and $5,000 per rack. For Sirius, we use single layer switches and tunable lasers, leading to lower power and hence lower cost. The total time taken for a message to fully travel from the sender to the receiver is brought down by 86% compared to an ideally electrical switched network. The system supports nanosecond granularity reconfiguration, enabling the handling of bursty cloud workloads very effectively. Additionally, usage of a single passive optical layer leads to a significant reduction in costs, about 75% lower when compared to an ideal electrically switched network. This slide goes over how Sirius behaves while under different kinds of loads. Under a low load, most flows transmit immediately without waiting for grants, and efficiency is quite high. Under a high load, more flows complete for limited slots, and there's some queuing and delay due to flow management and the scheduling overhead. But Sirius is still reasonably efficient under high loads. The initial request grant handshake introduces startup delay, but over a long transfer, that delay is amortized. So throughput remains strong for long flows. The queue size refers to how many flows or packets that can be stored while waiting for permission to send. If queue is too small, under high traffic, queues fill up quickly. New flows are dropped or delayed, hurting throughput and latency. On the other hand, if queue is large, more memory is needed. It can cause longer delays because older flows sit in the queue for longer. It has been found that a queue size of 4 gives the best trade-off between performance and efficiency. The study also investigates the impact of guardband size. A guardband is a small time buffer added between scheduled data transmissions to prevent collisions or interference. Smaller guardbands improve latency performance as they minimize the queuing delays caused by waiting at the intermediate nodes. Conversely, larger guardbands extend the epochs of transmission, worsening performance since packets wait longer before being sent. This highlights the importance of employing fast technologies to lower guardband sizes for enhanced network efficiency. Next, Rishabh is going to go over some advantages of this system.
Let's wrap up with everything we have explored about Cyrus and why this architecture represents a huge leap forward for the future of data center networks. So as we conclude, it gives us like nanosecond scale switching. So we know that traditional optical switches operate at millisecond or even microsecond scales, but this framework Cyrus it achieves 3.84 nanosecond reconfiguration latency using tunable lasers and caching techniques. Second one, co-design hardware and protocols. So routing, scheduling, congestion control, and even time synchronization are all designed with the physical hardware. This enables us with like such low latency and reliable behavior for the data centers. And then third, massive scalability and efficiency. So this framework can scale up to 24,600 racks. So that is like larger than the biggest data centers today. And it does this while reducing network power and cost by up to 77% compared to closed networks. Fourth one, future proof and tolerant. So because Cyrus uses a passive optical core, there is no dependency on CMOS or Moore's law scaling. And since it's robust, faults only degrade a small portion of network bandwidth, and thus the network can dynamically reconfigure around failures. So I'll be giving you like a two concept based examples, like firstly distributed deep neural network training. So let's suppose that we have a in a 1000 GPU training cluster, each GPU generates multiple terabytes of traffic. So this much of traffic traditional networks cannot handle and can't switch that much fast. But Cyrus can reconfigure optical paths at nanosecond granularity, keeping GPUs fed without wasting cycles. Second example is like disaggregated memory access. So when memory and computer are physically separated, so accessing the memory becomes latency sensitive. But this framework ensures that data moves between CPU and memory racks fast enough to feel almost that it's local only. So few of the drawbacks which we could come up with are like firstly, this framework adds one extra hop to every communication. So it basically increase end-to-end latency and create dependency on intermediates. So overall, this could degrade performance for latency sensitive flows like short RPCs, that is remote procedural cells or real-time analytics. Second drawback is it could be challenging in multi-tenant cloud environments. And the third one, the components like lasers are non-trivial to build, so it may be expensive and require tight calibration for this type of framework. Thank you.